Perhaps the most popular probability distribution is the normal one, also known as the Gaussian Bell Curve. Interestingly, it was not Gauss who originally formulated it, but rather popularized it. The distribution was actually developed by a French mathematician named Abraham de Moivre. The normal distribution has both ardent supporters and critics. Many of us likely recall our college statistics courses where this distribution was presented as a foundational probability tool. The normal distribution requires two parameters, mu and sigma, representing the mean and the standard deviation of a data sample, respectively. So the mean, mu, this is the sample average of all elements in a list. And the standard deviation, sigma, this is the measure of variability that represents the average deviation of all points in a sample from the mean. With these two data parameters, and assuming a sufficient data set, we can construct a symmetric probability distribution. This symmetry means that the central point, the mean, is equal to the mode and it is equal to the median. And the data points are evenly distributed on either side of a perfectly symmetrical bell curve. Now, real-world experiences show that most systems are not symmetric, making the normal distribution less applicable outside of theoretical examples. Although the normal distribution is based on the central limit theorem, a foundational principle in probability, it is valid only under very specific conditions. In its simplest form, the central limit theorem states that if we sum independent and random elements, their cumulative distribution will eventually converge to a normal distribution. While this is true for certain scenarios, such as opinion polls or surveys, many real-world systems deviate significantly from this pattern. For instance, power law distributions often feature asymmetric or heavy tails, meaning that the probabilities of extreme events are much higher than what a normal distribution would predict. Among the notable critics of the normal distribution is Nassim Taleb, the author of the bestseller The Black Swan. In his book, he dedicates a whole chapter titled The Great Intellectual Fraud to criticize the over-reliance on the normal distribution. Taleb argues that events like the 2008-2009 financial crisis were partially caused by the misguided assumption that financial market variations followed a normal distribution. This crisis demonstrated that financial systems do not necessarily behave that way. Now, there are certain issues with the normal distribution in operational and project risks. For operational and project risks, the normal distribution is often unsuitable for two key reasons. First, dependence on data. Calculating the standard deviation requires historical data, which is often unavailable in project contexts. While the mean is relatively easy to determine, the standard deviation often requires a robust data set. And then negative values. Consider a normal distribution with a mean of 1,000 and a standard deviation of 600. This configuration results in a significant probability of negative values, which is illogical in real-world risk scenarios. By nature, risks have a positive magnitude beginning at 0. This makes the normal distribution an illogical choice for modeling monetary impacts in operational or project risks. But there's an alternative. The log normal distribution, often described as the close relative to the normal distribution, addresses many of these shortcomings of its counterpart. In the next module, we will explore the log normal distribution and discuss how it effectively models monetary impacts in operational and project risks.